In power systems, many theorems from electrical engineering and circuit theory are applicable. These theorems are essential for analyzing power flow, stability, and optimization in electrical grids. Below is a list of the key theorems involved in power systems. Let us discuss top 100 of these theorems, laws and formula. Ohm's law: the current through a conductor between 2 points is directly proportional to the voltage across the 2 points and inversely proportional to the resistance. Kirchhoff's laws: current law KCL, the sum of all currents entering a node or junction is equal to the sum of all currents leaving the node. Kirchhoff's voltage law KVL, the sum of the electrical potential differences voltage around any closed network is zero. Thevenin's theorem: any linear electrical network with voltage and current sources and resistances can be replaced at terminals A and B by an equivalent voltage source in series with a resistance. Application in power systems helps simplify networks for easier analysis of power delivery, fault analysis, and load calculations. Norton's theorem: any linear electrical network can be replaced by an equivalent current source in parallel with a resistance at terminals A and B. Application in power systems: it is often used for simplifying complex circuits in fault and load flow studies. Maximum power transfer theorem: a load will receive maximum power from a network when the load resistance is equal to the Thevenin or Norton resistance of the network as seen from the load terminals. Application in power systems ensures that loads are matched to the system for optimal power transfer, such as in transmission line design and transformer sizing. Superposition theorem: in a linear network with multiple independent sources, the current or voltage at any point in the network can be found by algebraically summing the contributions of each source acting independently, with all other sources replaced by their internal impedances. Application in power systems, useful for analyzing networks with multiple sources, like generators in a power grid. Millman's theorem: in a network of parallel branches, each branch with its voltage source and impedance, the voltage across the parallel combination can be found by a weighted sum of the voltages divided by the sum of the conductances. Application in power systems, often used for simplifying the analysis of parallel circuits in power distribution. Telegen's theorem: for any electrical network, the sum of the power delivered by all sources is equal to the sum of the power absorbed by all elements. Application in power systems, important for energy conservation principles and power balance in a network. Load flow theorems and algorithms, Gauss-Seidel method, an iterative technique to solve the power flow equations in a power system. Application, commonly used in power flow studies to determine bus voltages and power flows in large networks. Newton-Raphson method, a more efficient and faster converging iterative method for solving nonlinear power flow equations. Application, widely used in large-scale power systems for load flow analysis due to its accuracy and speed. Fast decoupled load flow method, a simplified version of the Newton-Raphson method, where the Jacobian matrix is approximated to speed up calculations. Application, used in real-time power flow studies where speed is critical. Boucherot's theorem or power factor correction theorem describes how to adjust the power factor of a system to minimize losses and improve efficiency by introducing capacitors or inductors. Application in power systems, widely applied in the design of systems to reduce reactive power and improve power factor. bus matrix theorem: in a power system, the bus impedance matrix bus relates bus voltages to injected currents. Application in power systems, essential in fault analysis and short circuit studies. Swing equation theorem: the swing equation relates the power angle difference between rotor angle and synchronous reference and rotor dynamics in synchronous machines. Application in power systems, used in stability studies, especially transient stability analysis of generators and power systems under disturbances. Equal area criterion, a graphical method to determine the stability of a synchronous machine connected to an infinite bus under transient disturbances. Application in power systems, used in transient stability studies to assess whether a generator remains in synchronism after a disturbance. Thevenin-based fault analysis theorem: in fault analysis, the system can be simplified using the Thevenin equivalent to calculate fault currents and post-fault conditions. Application in power systems, essential for analyzing fault conditions such as short circuits in the network. The law of conservation of energy or first law of thermodynamics: energy cannot be created or destroyed, only transformed from one form to another. Application in power systems, fundamental in energy balance studies, particularly in power generation and consumption. Symmetrical components theorem. Any unbalanced set of three-phase quantities can be resolved into three sets of balanced components: positive sequence, negative sequence, and zero sequence. Application in power systems, extensively used in fault analysis, especially in unbalanced faults like line-to-ground or line-to-line faults. Ferranti effect theorem. In a lightly loaded or open-ended long transmission line, the receiving end voltage becomes higher than the sending end voltage due to the capacitive nature of the transmission line. Application in power systems, important in transmission line analysis and reactive power management. Lagrange's multiplier theorem, a method for finding local maxima and minima of a function subject to equality constraints. Application in power systems, used in optimal power flow OPF problems for the economic dispatch of generation resources while considering network constraints. Gauss's law for electricity. The electric flux through any closed surface is proportional to the total electric charge enclosed within the surface. Application in power systems, used in understanding electric fields around conductors and in transmission systems. Coulomb's law. The electrostatic force between two charges is directly proportional to the product of their charges and inversely proportional to the square of the distance between them. Application in power systems, important in analyzing capacitance and electric field distributions in transmission lines. Nyquist stability criterion. The Nyquist criterion is used in control theory to determine the stability of a closed-loop system based on the open-loop frequency response. Application in power systems, used to assess the stability of power system controllers, especially in automatic generation control AGC and power system stabilizers PSS. Lyapunov stability theorem. A system is said to be stable if there exists a Lyapunov function that is positive definite and its time derivative is negative definite. Application in power systems, applied in stability analysis, especially for determining whether a power system remains stable following small or large disturbances. Perron-Frobenius theorem. In a positive square matrix, there exists a unique largest real eigenvalue, the Perron root, and the corresponding eigenvector has strictly positive components. Application in power systems, used in power grid stability studies, including eigenvalue analysis for small signal stability and voltage stability. Bode stability criterion. The Bode stability criterion uses the Bode plot to determine the stability of linear, time-invariant LTI systems by looking at the gain and phase margins. Application in power systems, applied in control system design for stabilizing power system controllers such as voltage regulators and excitation systems. Synchronous machine swing equation. The swing equation governs the dynamic behavior of a synchronous machine's rotor angle relative to the reference, accounting for mechanical input power, electrical output power, and inertia. Application in power systems, central to transient stability studies, it helps to analyze the dynamic response of generators after disturbances such as faults. Frequency response theorem. Frequency response theory analyzes how a power system reacts to changes in load or generation that affect system frequency. Application in power systems, critical in designing frequency control systems such as governors and automatic generation control AGC to maintain system frequency within acceptable limits. Ralph Hurwitz stability criterion, a criterion to determine the stability of a linear system by analyzing the signs of the coefficients in the characteristic equation. Application in power systems, used to check the stability of control systems in power networks, such as generator excitation control and load frequency control. State space theorem. The state space representation expresses a system of first-order differential equations describing a dynamic system. It is used to model and analyze multi-input and multi-output systems. Application in power systems, used in modern control theory, dynamic modeling of power systems, and optimal control strategies like model predictive control MPC. Modal analysis theorem. Modal analysis involves decomposing a system into its natural modes of oscillation, each described by an eigenvalue and eigenvector. Application in power systems, used in small signal stability analysis, particularly in detecting oscillatory modes in power systems and improving damping through power system stabilizers PSS. Ziegler-Nichols tuning method, a method used to tune PID controllers by setting proportional, integral, and derivative gains based on a step response. Application in power systems, used in tuning controllers for power system elements like automatic voltage regulators AVRs and turbine governor systems. Lagrangian duality theorem. Lagrangian duality is a powerful framework in optimization where the problem is reformulated to find solutions that satisfy certain constraints while minimizing or maximizing an objective function. Application in power systems, central to optimal power flow OPF problems, economic dispatch, and unit commitment by optimizing the cost of power generation subject to system constraints. Minimum cut set theorem. In a network, a cut set is a set of edges whose removal disconnects the network. The minimum cut set theorem provides the minimum number of lines or elements that, when removed, disconnect the power flow. Application in power systems, used in reliability studies, security analysis, and contingency planning to evaluate the robustness of power grids. Nodal admittance matrix IBUS theorem. The IBUS matrix relates bus currents to bus voltages in a power system, where each element represents the admittance between buses. Application in power systems, fundamental and load flow studies, fault analysis, and power system modeling. Optimal power flow OPF theorem. The optimal power